Hello everyone and welcome back. In this video we will look at an interesting snippet of code and the outputs from two different compilers, and we'll make note of key differences between the storage of string literals. Here is a sneak peek of what we'll be getting into. We'll have some sort of code on the left hand side, the assembly version of that code in the middle, and then the standard output of the code on the right. For those of you that are new or have been following along, we'll be talking about pointers and strings in this video, so a little bit more on the intermediate side of C. But nonetheless, let's go ahead and explore the code. Alright, so here we have the snippet of code here, dupe1.c, and I've modified it just slightly to include the standard IO header since I was getting a couple errors here when I was trying to compile the code. So here what we see is we initialize the character pointer p to the string literal hello. We then go ahead and print the actual string as well as the address of hello using the pointer p. We'll then again assign p to the string literal goodbye. So definitely a new string there. We'll go ahead and print the string and the address of goodbye. And finally we'll reassign p to the string literal hello. So once again we'll be assigning it to another string, potentially version of different hello, but we'll see. And once again we'll print out that string again and the address, and we'll see how this can vary between different compilers, but curious to see what will happen here on my computer when we have string pointed to first hello, then goodbye, and then what would be hello again, whether or not that's the same string from line 6 or if from line 13 it's a whole new version or a whole new copy of the hello string. So let's go ahead and compile this real quick. Alright, so here we have a version of Windows Subsystem for Linux open, so you can go ahead and use the version of GCC I have installed here. Let's just confirm what kind of version we have of GCC. So here we can see we have version 9.3.0, which is a little bit outdated given that I believe the most recent version is back 15 major. But nonetheless, this should be ample or sufficient enough to go ahead and show the result of running our code. So we do GCC and do, noting here we're just using the default compiler flags that GCC provides. We're not providing any other additional compiler flags. We do get a couple of warnings, which are okay. We're going to go ahead and just ignore them for now. And running our dupe code here, we can see that hello's address is at this hexadecimal representation. So we're noting here we're at 7A2C3004. When we go ahead and see goodbye's address, once we've already allocated in the data section of the file, we see that we're at 7A2C3020. And once again, going back and printing out hello's address from line 13 here. So once again, once we reassign p back to hello after assigning it to goodbye temporarily, we can see that the address again is 7A2C3004, which is the same address as the hello from line 6. So we can see here that from this version, the compiler went ahead and kept one copy of the string hello and just moved the pointer around whenever we wanted to reassign the pointer. But nonetheless, we had one single instance of the hello string at this address of 7A2C3004. This may not always be the case, and we'll see right now shortly how a different compiler can actually create two copies of this string and leaving it up to the designer, the developer, to go ahead and incorporate such compiler flags or options such that you're able to only have a single copy of a single string rather than multiple copies of multiple strings in your code. So one tool I like to use a lot when I'm trying to visualize the actual code execution is this Python tutor here, where you can go ahead and copy and paste the language of your programming code here, select the language in which your code has written. In this case, we wrote it in C, so we're going to be using C17 plus GNU extensions that is provided by this Python tutor site. And once you have your code there and you selected the appropriate language, you can go ahead and click Visualize Execution. And this will give you a nice line by line code showing you exactly what's going on in your code. On the right side of the code here, we can see we have little different segments here. We have a little place for the stack, so we can actually see, as variables are getting allocated on the stack, we can see that they're going to show up in this part of the code or this part of the site here. If we have any variables that are on the heap, we'll see them appear here. In this text box right here, we'll see any printf calls or any standard output calls that we have in our code. And here we have options of seeing different kinds of views. In this case, we're going to show memory addresses, so we can actually see the addresses as P changes from different strings as we go ahead and go line by line through our code. So now here on the left hand side, we're going to go ahead and click next and just go line by line to see how each line is executed. So we can see on line 6, we have the car pointer or char pointer P points to the string literal hello. Here, make a note that the string hello is not in the heap, it's in the read-only storage. Recall that string literals are stored in the read-only data section of the binary file. Particularly if you're working with Linux, they'll appear in like the ELF file, if you've heard of that term. But nonetheless, we can see here that the pointer P points actually to the first character of the string literal, in this case H. And once again, this is the string terminated by the null termination character here. Now if we go ahead and print this string out, we'll see hello, and we'll see the addresses once again 400614 as we see here from the stack here. Now going into line 10, we can see that now we're going to reassign pointer P to the string literal goodbye. We can see here that now the address has changed. We see now the address is 400630, which is the address of the string character G of the string literal goodbye. So we can see here that we've moved the pointer to point to a different string now. Note that the string is still in the read-only storage of our binary file. Going off to do call the print call again on line 11, we can see we print goodbyes. Goodbyes address is 400630 as we see here. And last but not least, if we go ahead and reassign the pointer P back to the string literal hello, we can see once again that the address goes back to 400614, which is pointing to the character H of the string literal hello. And once again, if we go ahead and do a last print call here, you can see that hello's address is once again 400614. So we can see here, visualizing this code here with C17 with the GNU extensions from this Python tutor site, we can see once again that we have a single copy of the hello string in the read-only storage, and a copy of goodbye string again in the read-only storage. So we can see here that even though we've assigned pointer P at line 6 to point to the string hello, and then once again having it point to string hello again on line 13, the compiler goes ahead and creates a single instance or a single copy of the string, and then we're able to go ahead and reference that string whenever we run into assigning P back to the string or using the actual string in our actual code. Alright, and now we'll try to compile the same block of code that we have previously, but now using a different compiler. In this case, we're going to be using MSCBC's version 19.43 provided to us by godbolt.org. Here we can see on the left hand side we have the same C file here, the same code that we have in the C language. In the middle file here we have the compiler standard output as well as the program standard output. And on the right hand side here we have the assembled output of the code and assembly language instructions. Make a note here, now we're going to see the actual output. In the middle here, once we've run or compiled this code with no compiler options, we can see that the address of hello is at the hexadecimal representation of 0x3cb000. When we assign the pointer P to point to the string literal goodbye, we see that goodbye's address is at 0x3cb020. And then once we reassign pointer P back to the string literal hello on line 13, we can see that hello's address is now at 0x3cb040, which is an offset now of 40 hex from the previous address that we had on line 6 when we first assigned pointer p to the string literal hello. Now this is further shown or further reflected here if you look at the actual assembled output. We can see on the right hand side in the data segment block here that we have several copies of several strings. Specifically here on line 8 we have the first copy of the string literal hello, which is referenced by the SG9726 offset here. Going on to line 10 we have the string that we pass into the printf call. Going on to line 12 we have the string literal of goodbye being offset by SG9728, and again the string that gets passed into the printf call post the reassignment of pointer p. And last but not least, here on line 15 we see the second copy of the hello string referenced at SG9730 offset. Last but not least, we have the third copy of the string that we pass into the printf call here at SG9731. If you were to scroll down here into the main section block, which is representative of the main function here, we can see that the Godbolt compiler gives us a nice color-coded scheme to actually see the actual line-by-line assembly instructions as they're represented by their higher level language calls on the left-hand side here of the C file. Nonetheless, we can see that in the yellow line here, when we first assign pointer p to hello, we're using the offset of 9726, which is the first copy of hello. When we go to line 10, which is the darker orange here, we can see that now we're referencing we're assigning pointer p to the string goodbye, which is offset by the 9728 string, which is this reference right here. And last but not least, once we reassign pointer p to the string hello, in the lighter orange, we can see that now we're referencing the string at SG9730, which is the second copy of hello. And then finally, we can see, again, to recap here in the data segment, we have 3 different copies of this string that we pass into the printf call. So we can see we have a total of 6 different strings in the data segment for the MSVC's compile output with no compiler options. So we can see as compared to GCC, by default, we'll have duplicate copies of strings in our data segment. Now we have the option of turning this off by providing a compiler flag to the MSVC's compilation commands. More specifically, we can pass in the \gf, which is known as the string pooling or the elimination of duplicate strings. This will make sure that the compiler creates a single copy of identical strings within the program image in memory during execution. And we have the option of doing that by passing in compile options here in the compiler explorer. So passing GF here, and we can see that the output has changed. We can see now that hello's address initially is at 0x1014.160, and then on the third line of the standard program output, we see that hello's address is back at 0x1014.160, so the same address here. Passing in the same compile flag to the compile output to see the compiled assembled output, so \gf. We can see in the data segment now here we have only 3 strings. We have the goodbye string, we have the string that we passed into the printf call, and we can see now we have only a single copy of the hello string. So we can see by enabling this compile flag \gf, we went ahead and had initially 6 strings, and now we have 3 strings. So we went ahead and optimized, allowing MSVC to only create a single copy of the hello string as well as the string that gets passed into the printf call here. And we can see total that now we've essentially truncated the actual output or the compiled output of the assembled language. But nonetheless, to recap, we can see that we have the option of eliminating duplicate strings with MSVC, but in terms of other compilers such as GCC, we get that option by default. But nonetheless, it's always nice to check your compiler's implementation to make sure that you're not creating multiple copies of multiple strings and therefore cluttering or making your data segment way larger than it needs to be. Thank you all for watching. If you like this video, please give it a thumbs up. And of course, feel free to share it amongst your friends. And as always, if you like this type of C programming content, give that subscribe button a click, and I'll catch you in the next video.